Take a proton, one of the particles sitting inside every atom in your body, and try a simple experiment on paper. It is built from 3 tiny quarks, so add up their masses. 2 up quarks, 1 down quark. Do the arithmetic carefully. And here is where everything falls apart. Those 3 quarks account for barely 1% of the proton's actual mass. 99% of it is simply gone, unexplained, absent from your calculation. The matter that makes up mountains, oceans, planets, and people is almost entirely built from something with no obvious source. So where is that mass hiding? What is it made of, if not the particles we are told the proton contains? The answer is one of the strangest truths in all of physics, and it means most of your weight does not really matter at all. Before we go further, if you find these kinds of deep dives into the hidden machinery of reality worthwhile, a quick like or subscribe really does help this channel keep growing. It is a small thing for you, but it means a lot to me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. There is a number you can calculate right now in your head that should give you the mass of a proton. It is one of the simplest ideas in all of physics. A proton, the positively charged particle sitting at the heart of every atom in your body, in every breath you take, and in every star in the sky, is made of 3 smaller particles called quarks. 2 of them are up quarks. 1 of them is a down quark. To find the mass of the whole proton, you would think, you simply add the masses of its pieces. 3 quarks. Add them together. Done. So let us do exactly that. Physicists have measured the masses of these quarks with extraordinary care. An up quark has a mass of about 2.2 mega-electron-volts. That is just a unit physicists use to measure tiny masses, the same way you might use grams or pounds, only scaled down for the subatomic world. A down quark is a little heavier, about 4.7 mega-electron-volts. A proton contains 2 up quarks and 1 down quark. So we add them. 2.2 plus 2.2 plus 4.7. The total comes to about 9 mega-electron-volts. Now here is the measured mass of the actual proton, the real thing, the number you get when you weigh it in a laboratory. It is about 938 mega-electron-volts. Stop and look at those 2 numbers side by side, 9 and 938. The pieces add up to 9, but the whole thing weighs 938. The 3 quarks account for roughly 1% of the proton's mass. 1%. Where is the other 99%? It is not a rounding error or a small discrepancy that better measurements will clean up. It is almost the entire mass of the proton, simply unaccounted for. And since protons and neutrons make up essentially all the mass of every atom, and atoms make up you, this missing 99% is not some abstract curiosity. It is most of your body weight. It is most of the mass of the chair you are sitting in, the ground beneath you, the planet, the sun, the galaxy. The overwhelming majority of the mass of everything you have ever touched comes from a source that the simple 3 quarks added together picture cannot explain at all. This is one of the deepest and most beautiful puzzles in modern physics, and tonight we are going to solve it. We are going to find out exactly where the proton gets its mass, and the answer is going to be far stranger, far more wonderful than 3 little balls stuck together. To find the missing mass, we first have to throw away the picture almost everyone carries in their head. When you imagine an atom, you probably picture something like a tiny solar system. A small clump in the center, the nucleus, with even smaller dots, electrons, circling around it. And if you zoom into that central clump, into a single proton, you probably picture 3 little spheres sitting quietly together, maybe touching, maybe slowly drifting around one another like marbles in a bag. 3 quarks, calm, static, solid. That picture is not just incomplete. For understanding mass, it is wrong. And the 3 quarks we have been talking about, the 2 ups and the 1 down, even have a special name to mark how partial they are. Physicists call them the valence quarks. That word, valence, is borrowed from chemistry, where it describes the outermost electrons that determine how an atom bonds. Here it means something similar. The valence quarks are the defining quarks, the ones that give the proton its identity, its electric charge, its character. They are the reason a proton is a proton and not something else. But, and this is the crucial point, they are not the only things inside. They are not even close to being the only things inside. Calling the proton 3 quarks is like calling a thunderstorm 3 raindrops. It names something real, but it misses the storm entirely. It is worth being precise about what the 3 valence quarks succeed in explaining, because their success in one arena is exactly what makes their failure in another so striking. The valence quarks explain the proton's electric charge perfectly. An up quark carries a charge of positive 2/3 in the units physicists use, and a down quark carries a charge of negative 1/3. 2 ups and 1 down give 2/3 plus 2/3 minus 1/3, which comes to exactly positive 1, the measured charge of the proton, which is precisely correct. The valence quarks also explain the proton's identity, why it is a proton and not a neutron. Swap one of the up quarks for a down quark, giving 1 up and 2 downs, and the charge becomes 0, and you have built a neutron instead. The 3 valence quarks, in other words, are spectacularly successful at accounting for the proton's charge and its identity. On these questions, the simple picture works flawlessly, which is precisely what makes the mass so jarring. The very same 3 quarks that nail the electric charge to perfection fail by a factor of 100 to account for the mass. They get the charge exactly right and the mass almost entirely wrong. This is the signature of a deep truth. It tells us that charge and mass have completely different origins inside the proton. Charge is a simple, additive property carried by the valence quarks, and it adds up cleanly. Mass is not additive at all, not a sum of pieces, but something that emerges from the energy of the whole churning system. The same particles that explain one property cannot explain the other, because the 2 properties come from entirely different places. Charge comes from the quarks. Mass, as we are about to discover, comes from the storm. So what is actually inside a proton? What does the storm look like? To answer that, we have to understand that a proton is not a quiet container. It is a region of space about 1 femtometer across, which is 1 quadrillionth of a meter, so small that you could line up roughly 100 billion of them across the width of a single human hair. And inside that almost unimaginably tiny volume, there is a frenzy of activity happening at speeds approaching the speed of light. The proton is not a bag of 3 marbles. It is a churning, boiling, roaring interior, more like the heart of a furnace than a box of objects. Let us start with the 3 valence quarks, because they are still there, and they are still important. But the first thing that has to change in your mental picture is that these quarks are not sitting still. They are moving, and not gently. They are confined inside that femtometer-wide space, trapped, and being trapped in such a tiny region forces them to move at tremendous speeds. This is a consequence of quantum mechanics. When you confine a particle to a very small space, you force it to have a large range of possible momenta, which means it carries enormous energy of motion. The smaller the box, the more violently the trapped particle must move. And the proton is one of the smallest boxes in nature. So the valence quarks inside are not drifting. They are tearing around at relativistic speeds, carrying energy of motion that is far greater than the tiny energy locked up in their rest masses. Already, this should make you pause. We added up the rest masses of the quarks and got 9. But the quarks are also moving, and moving things carry energy. Hold on to that thought, because energy is going to become the hero of this entire story. But moving quarks are only the beginning. They are not even the strangest part. The second thing inside the proton is something that almost no one outside of physics has ever heard of, and it is genuinely bizarre. It is called the sea. Not water, of course, but a sea in the sense of something vast and constantly shifting. The interior of the proton is filled with quark-antiquark pairs that flicker into existence and then vanish, over and over, trillions upon trillions of times, faster than you could ever hope to measure any single one of them. These are sometimes called sea quarks, to distinguish them from the three valence quarks. They are not permanent residents, they are temporary. They are born from energy, live for an almost infinitesimal slice of time, and then annihilate back into energy, while new ones are already appearing to take their place. This sounds like science fiction, but it is a direct consequence of well-tested physics. In quantum mechanics, empty space is never truly empty. The vacuum itself seethes with what physicists call fluctuations. Because of the uncertainty principle, energy can be briefly borrowed from nothing and used to create a particle and its antiparticle partner, as long as that pair pays the energy back almost instantly by annihilating. This happens everywhere, all the time, even in the emptiest void between galaxies. But inside the proton, where the strong force is screaming and energy is densely packed, this process is supercharged. The interior is a thick, roiling sea of quark-antiquark pairs constantly appearing and disappearing. At any given instant, a proton does not contain three quarks. It contains the three valence quarks plus an indeterminate, fluctuating, ever-changing number of additional quarks and antiquarks. If you could take a single snapshot of a proton and freeze it in time, you might find 5 quarks and 2 antiquarks. Take another snapshot a moment later, and you might find 7 quarks and 4 antiquarks. The number is never fixed. The proton is a crowd that is always changing its membership while keeping its overall identity intact, because the 3 valence quarks are always there in the bookkeeping, defining what the whole thing is. And the scattering experiments revealed something even more startling than the mere existence of quarks, something that deepens the mystery rather than resolving it. By firing electrons at protons over and over, millions upon millions of times, and studying exactly how the electrons scattered, physicists could work out not just that there were constituents inside, but how the proton's internal momentum was shared among them. They could measure, in effect, who inside the proton was carrying how much of its energy and motion. And the result overturned the simple picture entirely. If the proton really were just 3 quarks, those 3 quarks should carry essentially all of the proton's internal momentum among themselves, essentially. There would be nothing else inside to carry any. But the experiments found something different. When physicists added up all the momentum carried by all the quarks and antiquarks inside the proton, the quarks and antiquarks together, the total came to only about half of the proton's momentum, roughly half. The other half was simply not being carried by any quark or antiquark at all. It was being carried by something else, something electrically neutral that the electrons could not strike directly, and so could not see in the same way. That something was the gluons. Fully around half of the proton's internal momentum is carried not by quarks of any kind, but by the gluon fields binding the whole thing together. The glue, it turned out, was not a thin background layer. It was carrying as much of the proton's momentum as all the quarks and antiquarks combined. This was a profound clue, pointing exactly where our story has been heading. The proton is not 3 quarks with a little glue holding them in place. It is a system in which the binding fields themselves are a dominant component, carrying a vast share of the internal energy and momentum. The gluons are not a detail. They are half the story by this measure. And, as we will see, they are even more central when we turn from momentum to mass. And there is a third population inside the proton, perhaps the most important of all for our mystery, and we have not even named it yet. Because here is the question that should be nagging at you. If the proton is so violently energetic, if the quarks are tearing around at near light speed and trying to fly apart, what is holding the whole thing together? What keeps this storm from simply exploding outward and scattering its contents across the universe? Something must be binding it. Something must be gripping those quarks and refusing to let them escape. And whatever that something is, it must be powerful beyond anything in everyday experience. That something is the strong force, and it is carried by particles called gluons. The name is almost charmingly literal. Gluons are the glue. They are the particles that pass between quarks and carry the strong nuclear force, the force responsible for holding the quarks together inside the proton. Without gluons, there would be no protons, no atoms, no chemistry, no planets, no us. They are the binding agent of ordinary matter. But the gluons are not a passive background. They are not like cement that gets poured once and then sits there hardening. The interior of the proton is densely, overwhelmingly populated with gluons, swarming between the quarks, being emitted and absorbed billions upon billions of times in every fraction of a second. The valence quarks are constantly throwing gluons back and forth, and the gluons themselves are doing something that no other force carrier in nature does. Something we will explore in detail later, but which is worth flagging now. Gluons interact with each other. They are not just messengers passing between quarks. They tangle with one another, emit more gluons, and form a dense and self-reinforcing web. The result is that the proton's interior is not mostly quarks at all. By many measures, the gluons and their fields are the most active, most energetic component of all. The three valence quarks that give the proton its name are, in terms of the ceaseless activity filling that tiny volume, a small minority presence amid a swarm of gluons and a churning sea of quark-antiquark pairs. So let us repeat what the proton actually contains, because this is the foundation of everything that follows. It contains the three valence quarks, 2 up and 1 down, confined yet never still. It contains a constantly fluctuating sea of additional quark-antiquark pairs, flickering in and out of existence. And it contains a dense, dynamic, self-interacting population of gluons, binding the whole thing together and filling the interior with intense fields of energy. This is the storm. This is what is really there. And now you can begin to see why the simple addition of 3 rest masses gave us the wrong answer by a factor of 100. We were counting 3 marbles. The reality is an inferno. But seeing the inferno is not yet the same as explaining the mass. We have to be very careful here, because it is easy to wave our hands and say, oh, there is a lot going on inside, so of course it is heavy, without actually understanding the mechanism. Physics is not satisfied with vague gestures. We need to understand precisely how a churning interior of moving quarks and massless gluons can add up to 938 mega-electron volts when the quarks themselves only contribute 9. And to get there, we first have to be absolutely clear about a distinction that lies at the very center of this whole puzzle. The distinction between 2 different things that, in everyday life, we lazily blur together. The distinction between rest mass and energy. When we said an up quark has a mass of about 2.2 mega-electron volts, we were talking about a very specific thing. We were talking about its rest mass, sometimes called its intrinsic mass or bare mass. This is the mass a quark would have if it was sitting perfectly still, doing nothing, in isolation. It is an intrinsic property of the particle itself, woven into what the quark fundamentally is. It does not depend on how fast the quark is moving or what is happening around it. It is the built-in mass of that single particle, considered all by itself. And these rest masses are genuinely tiny. The up and down quarks are among the lightest particles in all of nature. Their rest masses are almost negligible. That is why adding 3 of them together gives you such a small number. But rest mass is not the only thing that has weight, so to speak. And this is the idea that is going to unlock the entire mystery. Energy also contributes to mass. Energy and mass are not two completely separate things. They are deeply, fundamentally related, connected by the most famous equation in all of science, an equation almost everyone has seen and almost no one has been properly told what it means. Energy equals mass times the speed of light squared. We will spend real time later understanding exactly what that equation says and, just as importantly, what it does not say. But for now, hold on to its core revelation. Energy and mass are interchangeable aspects of the same underlying thing. Where there is energy, there is mass. Where there is mass, there is energy. They are two faces of one coin. And now think about what is inside the proton. Quarks moving at near light speed carry enormous energy of motion, energy that has nothing to do with their rest masses. The sea of quark-antiquark pairs flickering in and out of existence is pure energy, made temporarily into particles and then turned back into energy. And the gluons, swarming and tangling and binding, carry energy in their fields, energy stored in the very tension of the force that holds the proton together. The proton's interior is not just busy, it is bursting with energy. Kinetic energy, field energy, the energy of confinement. Energy upon energy upon energy, packed into a space 1 femtometer across. This is where the missing 99% has been hiding all along. Not in more particles we forgot to count, not in some heavier quark we did not know about. The missing mass of the proton is energy. It is the total energy of all that frantic internal activity, the moving quarks, the fluctuating sea, the swarming gluon fields, all of it bound up inside that tiny volume by the strong force. And because energy is equivalent to mass, that energy shows up on the scale as weight. The proton is heavy not because its parts are heavy, but because its parts are doing so much. The mass is in the motion. The mass is in the fields. The mass is in the storm. Now, I want to be very careful not to let that statement become a slogan, because slogans are where understanding goes to die. It is tempting to just say, mass is energy, the end, and walk away feeling satisfied. But that would skip over the genuinely fascinating question of how exactly this works. Why does a system of fast-moving, mostly massless ingredients end up with a definite, fixed mass of 938 mega-electron volts, the same for every proton in the universe? How can massless gluons contribute to mass at all? How can the energy of motion become permanent, weighable mass, rather than just fleeting kinetic energy? These are not questions we can answer by repeating energy equals mass louder. They require us to understand the actual machinery, the theory that governs this whole subatomic storm. And that theory has a name. It is called quantum chromodynamics, and it is one of the crowning achievements of 20th century physics. We will dive into that theory soon, and it will reward us richly. But before we do, I want to make sure the scale of what we have discovered is fully clear, because it is genuinely staggering, and it is easy to let it slip past. We tend to think of mass as something solid, something substantial, something made of stuff. You hold a rock in your hand and feel its weight, and that weight feels like a property of the material, of the matter packed inside it. But we have just discovered that this is, for the most part, an illusion. The weight of that rock is overwhelmingly not the weight of its quarks. It is the energy of the strong force raging inside every single one of its protons and neutrons. If you could somehow switch off all that internal motion and field energy and leave only the bare rest masses of the quarks, the rock would lose about 99% of its mass. The matter would still be there, in the sense that the quarks would still exist, but the weight would be almost entirely gone. Let that sink in. The solidity of the world, the heft of objects, the very mass that gives matter its presence, is mostly not matter in the way we imagine matter. It is bound energy. It is the strong force made tangible. When you step on a scale in the morning and read your weight, the number you see is, to about 99%, a measure of the energy locked inside the protons and neutrons of your body, the kinetic energy of confined quarks and the field energy of swarming gluons, all of it bound together and made permanent by the strong interaction. You are not mostly made of heavy particles. You are mostly made of energy that has been trapped and given the property we call mass. And I want to be equally careful to say what this does not mean, because there is a tempting wrong conclusion lurking nearby. This does not mean that mass is created from nothing. It is not magic. It is not something for nothing. The energy inside the proton is absolutely real and absolutely present. It costs something to assemble a proton. The energy is there, woven into the fields and the motion, governed by precise and unbreakable laws. Nothing is being conjured out of empty air. What is happening is subtler and far more interesting than creation from nothing. Energy that is real and present, the energy of fields and motion, manifests as the property we call mass when it is bound into a system. The proton's mass is not invented. It is the energy content of the proton, expressed as mass. There is a profound difference between mass comes from nothing and mass comes from energy that was always there. This story is firmly the second kind. There is one more piece we need to set in place before moving on, because there is a character in this story that almost everyone has heard of, and people often assume it is the answer to our question when it is not. That character is the Higgs field, and its discovery, confirmed in 2012, was one of the great triumphs of modern science. You have very likely heard the Higgs described as the thing that gives particles their mass, or even nicknamed the mass particle, or more dramatically, the God particle. And so it would be perfectly natural to assume that the Higgs is where the proton's mass comes from. Surely, if there is a field whose job is to give things mass, that must be the source of the missing 99%. But it is not. And this is one of the most widely misunderstood points in all of popular physics, so it is worth stating plainly right now and returning to in full detail later. The Higgs field is responsible for giving the quarks their rest masses. It is the reason the up quark has its 2.2 megaelectronvolts and the down quark has its 4.7. The Higgs field gives the fundamental particles their intrinsic, bare masses. But notice what that means in light of everything we have just learned. Those rest masses, the ones the Higgs is responsible for, are precisely the tiny numbers that add up to only 9 megaelectronvolts. The Higgs gives us the 1%. The Higgs is responsible for that small sliver of the proton's mass that comes directly from the quarks themselves. It has almost nothing to do with the other 99%. The overwhelming bulk of the proton's mass does not come from the Higgs field at all. It comes from the strong force, from quantum chromodynamics, from the energy of the bound, churning system. The Higgs hands the quarks their small starting masses, but almost the entire weight of the proton and of nearly all ordinary matter is built by the strong force alone. So we have arrived at the shape of our answer, even if we have not yet built the full machinery to prove it. The proton weighs about 100 times more than its quarks, because it is not really 3 quarks at all. It is a tiny, ferocious region of space packed with fast-moving quarks, a flickering sea of quark-antiquark pairs, and a dense swarm of gluon fields, all bound together by the strong force. The mass we measure is the total energy of that bound system, expressed through the equivalence of energy and mass. The quarks contribute their rest masses, a mere 1%, courtesy of the Higgs field. Everything else, the entire towering remainder, is emergent energy. It is the weight of the storm itself. But naming the answer is not the same as understanding it. We have said that energy gives mass, that gluons bind the quarks, that the strong force is the engine. Yet every one of those statements raises a harder question underneath it. Why can the quarks never escape? Why does the force holding them grow stronger, not weaker, the harder they try to flee, behaving like nothing else in the physical world? How do gluons, which have no mass of their own whatsoever, end up generating mass for the proton? And how, precisely, does the energy of motion and field become the fixed, unchanging mass that every proton in the cosmos shares to staggering precision? To answer those questions, we have to leave behind the simple picture entirely and step into the strange and beautiful rules of the strong force, the force that does not weaken with distance, the force that forges nearly all the mass of the visible universe. That is where the real machinery lives, and that is where we are going next. Take two ordinary magnets and try to pull them apart. As your hands separate them, you feel the pull weaken. The farther apart they get, the easier it becomes, until at arm's length you feel nothing at all. This is how every force in your everyday experience behaves. Gravity weakens with distance. The electric force weakens with distance. Magnetism weakens with distance. Move things apart and the grip relaxes. This is so ingrained in our intuition that we never think about it. Of course, forces fade with distance. What else could a force possibly do? The strong force does the opposite. And that single, almost unbelievable fact is the key to everything we are trying to understand. Inside the proton, the force that binds the quarks together does not weaken as the quarks move apart. It grows. Try to pull two quarks away from each other, and the force holding them together increases, like a spring that gets stiffer the more you stretch it, or a rubber band that pulls back harder the farther you stretch it. There is no arm's length at which the grip relaxes. There is no distance at which the quarks finally come free. The harder you try to separate them, the more fiercely the strong force fights back. This is the strangest force in nature, and it is the force responsible for nearly all the mass of the visible universe. Tonight we are going to understand how it works, and in understanding it, we are going to see exactly how the proton becomes a roaring engine of bound energy. To begin, we need to understand what the strong force is actually responding to. Gravity responds to mass. The electric force responds to electric charge. Positive and negative charges attract, as charges repel, and the strength depends on how much charge is present. The strong force works in a roughly similar spirit, but it responds to a completely different property, a kind of charge that has nothing to do with electricity, and that only quarks and gluons possess. Physicists, in a fit of whimsy, decided to call this property color. Now, this is important. This color has nothing to do with the colors your eyes see. A quark is not literally red or green or blue. The name is a metaphor, a label, a piece of vocabulary chosen because the rules of how this charge combines happen to resemble, loosely, the way colors of light mix together. So when physicists say a quark carries color charge, they mean it carries the specific kind of charge that the strong force responds to, in the same way that an electron carries the electric charge that the electromagnetic force responds to. Color charge comes in three varieties, whimsically named after three colors. And the deep rule of the strong force is that nature insists everything we can actually observe must be color neutral. It must have no net color charge at all, in the same way that an atom as a whole is electrically neutral. This single rule the demand for color neutrality, is the seed from which confinement grows. A single quark carries a color charge. It is not neutral, and nature will not permit a lone, color-charged quark to exist freely, drifting through space on its own. It must always be combined with other quarks or antiquarks in such a way that their colors cancel out to neutrality. A proton works because its 3 quarks carry 3 different colors that together add up to neutral, just as 3 particular colors of light combine to make white. The proton is color neutral overall, even though each quark inside it is not. And that is the only reason the proton is allowed to exist as a free particle. It has hidden its color charge by balancing it perfectly internally. There is also a second way nature can build something color neutral, and it is worth knowing because it connects the proton's story to the larger structure of every atom. Alongside the 3 colors of charge, there are 3 matching anticolors carried by antiquarks. And just as a color and its anticolor cancel to neutrality, the way a positive and a negative electric charge cancel, a single quark can pair with a single antiquark carrying the matching anticolor, and together they form a color-neutral particle. These quark-antiquark pairs are a whole family of particles in their own right, called mesons. So there are 2 fundamental recipes for color neutrality. 3 quarks of 3 different colors, which give you a proton or a neutron, or 1 quark and 1 antiquark of matching color and anticolor, which gives you a meson. This is not a side note. The lightest mesons, called pions, are the particles that flit between protons and neutrons inside an atomic nucleus and bind them together. The same strong force that confines the quarks inside a single proton, reaching just slightly beyond the proton's edge, is what holds the entire nucleus together. The force that builds the proton's mass is, in a leftover, residual form, the very force that assembles every atomic nucleus in the universe, and so every atom, and so everything. But why should this lead to a force that grows with distance? Why should color neutrality be enforced so violently? To understand this, we have to look at the gluons, and at the one property that makes the strong force utterly unlike any other force in nature. We touched on it before, but now it becomes central. Gluons carry color charge themselves. This sounds like a small technical detail, but it changes everything. Consider the comparison with electromagnetism. The electric force is carried by photons, particles of light. But a photon has no electric charge of its own. It is electrically neutral. This means photons do not interact with each other. 2 beams of light pass straight through one another without the slightest effect. Shine 2 flashlights so their beams cross, and nothing happens at the crossing point. The photons ignore each other completely, because neither one carries the charge that the other one responds to. The messengers of the electric force are blind to each other. Gluons are not like this at all. Because gluons carry color charge, gluons respond to the strong force. They feel it. They pull on each other. They emit and absorb more gluons. The messengers of the strong force are not blind to each other. They grab each other. And this self-interaction of gluons is the single most important fact in this entire story, because it transforms the strong force from something tame into something ferocious. In electromagnetism, the field lines connecting 2 charges spread out into space, fanning apart, which is precisely why the force weakens with distance. The lines dilute as they spread. But the gluon fields connecting 2 quarks do not spread out and dilute. The gluons, because they attract each other, pull the field lines together. They bundle them. They refuse to let the field fan out into space. And the result is one of the most remarkable structures in physics. Instead of spreading out, the strong force field between 2 quarks collapses into a narrow tube. Physicists call it a flux tube, or sometimes, more vividly, a string. Imagine the field lines, instead of fanning outward like the spokes of a wheel, being squeezed together into a tight, taut rope of pure, strong force field, stretching directly from one quark to the other. This is the flux tube. It is a concentrated channel of intense energy, held together by the gluons' insistence on clumping with one another. And because the field is confined to this narrow tube, rather than spreading out, something extraordinary happens when you try to pull the quarks apart. When you separate two quarks, you do not dilute the field between them. You cannot, because the gluons will not let it spread. Instead, you stretch the flux tube. You make the rope longer. And here is the crucial point. A flux tube has a roughly constant energy per unit of length. Every additional femtometer you stretch it costs the same fixed amount of energy. This is completely different from the electric case, where stretching the distance dilutes and weakens everything. The flux tube does not weaken. It just gets longer, and each new length of it stores the same energy as the last. The force you feel, the tension in this subatomic rope, stays roughly constant no matter how far you pull. And that constant tension is enormous. The tension in the flux tube inside a proton is on the order of 14 tons of force. 14 tons, concentrated in a tube stretched between two particles, each far smaller than an atom. To pull a single quark out of a proton, you would have to fight against a pull comparable to the weight of several cars, sustained across a distance you cannot even see. Now you can begin to see why a quark can never be isolated, why no one has ever caught a single quark alone, and why no one ever will. Suppose you tried. Suppose you grabbed a quark inside a proton and started hauling it away from its partners, fighting that 14-ton tension. As you pull, you stretch the flux tube, and stretching it costs energy, more and more energy, piling up in the lengthening rope. You are pouring energy into the tube with every femtometer of separation. And remember what we established earlier, energy and mass are equivalent. So as you stretch the tube and pump energy into it, that energy accumulates until it reaches a threshold. The threshold where there is enough energy stored in the tube to do something dramatic. At that point, the tube does not break to release a free quark. Instead, the energy in the stretched tube converts itself into a brand new quark and antiquark pair, materializing right out of the energy of the field. Exactly the kind of materialization we discussed when we spoke of the churning sea inside the proton. The new pair appears in the middle of the stretched tube. The antiquark rushes to pair with the quark you were trying to extract, forming a new color-neutral particle. The new quark stays behind with the others, and the tube snaps into two shorter tubes, each color-neutral, each perfectly stable. Think about what this means. You set out to isolate a single quark. You pulled and pulled, fighting tremendous tension, pouring in energy. And the moment you had pumped in enough energy, that energy simply manufactured new quarks, and instead of one free quark in your hand, you ended up with two color-neutral particles, and not a single isolated quark anywhere in sight. It is as if you tried to create a magnet with only a north pole by cutting a bar magnet in half, and instead of getting an isolated north pole, you got two complete magnets, each with its own north and south. The strong force does the same thing, but more violently and more strangely. You cannot get a lone quark, ever, because trying to extract one creates new quarks to keep everything color neutral. This is confinement. Quarks are confined, imprisoned, forever bound inside color-neutral combinations, and the prison walls are made of the strong force's growing tension and its boundless ability to convert energy into new particles. This is already a profound idea, but I want to make sure we feel the full weirdness of it, because it overturns the entire way we instinctively think about taking things apart. Throughout the history of science, the way you understood what something was made of was to break it into pieces and look at the pieces. Break a molecule into atoms. Break an atom into a nucleus and electrons. break a nucleus into protons and neutrons. At every level, you could separate the parts and study them individually. This is the most basic method of all reductionist science. Take it apart, examine the pieces. And it worked at every level, until physicists reached the quarks. At the level of quarks, the method simply stops working. You cannot take the proton apart and lay its 3 quarks on the table to examine them. The universe forbids it. Try to separate the pieces, and the energy of separation creates new pieces, so you never reach the isolated parts. The quarks are real. They are inside the proton. We have detected their presence in countless experiments, and yet they can never, even in principle, be pulled out and studied alone. They exist only in combination. They are parts that refuse to become separate. This is unlike anything in the macroscopic world, and it is the everyday reality of the strong force. You might reasonably ask whether confinement has ever actually been seen, or whether it is only an inference. It has been seen, in a sense, every single day in the most powerful particle accelerators on Earth, and the way it shows up is itself a vivid demonstration of everything we have been describing. When physicists smash particles together at enormous energies, they sometimes strike a single quark inside a proton so hard that it goes flying outward with tremendous speed, knocked clean toward freedom. For the briefest instant, it looks as though a quark might finally escape on its own. But it never does. As the struck quark races outward, it stretches a flux tube behind it, and that tube, as we have seen, fills with energy as it lengthens. The energy mounts until it snaps into new quark and antiquark pairs, and those pair up into color-neutral particles. The single escaping quark, in the act of trying to flee, manufactures a whole spray of ordinary particles out of the energy of its own attempted escape. What the detectors actually record is not a lone quark, but a narrow, focused jet of particles, all flying out roughly in the direction the quark was heading. Physicists call these sprays jets, and they are the unmistakable fingerprint of a quark that tried to escape and triggered confinement in the attempt. So when you knock a quark hard inside a collider, you do not get a free quark on your detector. You get a jet, a burst of color-neutral particles born from the energy of separation, fanning out along the path the quark was taking. The quark's existence and its direction are written clearly in the jet, but the quark itself never appears alone. Confinement is not merely a theoretical claim, it is a thing physicists watch happen in real time in their detectors thousands of times a day. Every jet is confined, caught in the act. But how could anyone possibly know what is inside a proton if a proton is a quadrillionth of a meter across and you can never crack one open to look? This is a fair and important question, and the answer is one of the great experimental stories of the 20th century. You cannot put a proton under a microscope, because no microscope built from ordinary light could ever resolve something so small. So physicists did something cleverer. They did to the proton exactly what an earlier generation had done to the atom. They shot things at it. Recall how the structure of the atom was first revealed. Physicists fired fast-moving particles at a thin foil and watched how they bounced. Most passed straight through, but a few ricocheted back at sharp angles, and that ricochet betrayed the presence of a tiny, dense core at the center of each atom, the nucleus. The pattern of how the projectiles scattered told the story of what was inside, even though no one could see the nucleus directly. The deflections were the fingerprints of hidden structure. In the late 1960s, physicists did the same thing to the proton, but with vastly more powerful machines. They accelerated electrons to enormous energies and fired them straight into protons, then carefully measured how those electrons scattered. If the proton were a smooth, uniform little ball of charge, the electrons would have been deflected gently and predictably. But that is not what happened. Every so often, an electron would come screaming out at a steep angle, scattered hard, as though it had struck something small and solid deep inside the proton. The proton, it turned out, was not smooth at all. It had hard, point-like things inside it, off which the electrons occasionally bounced sharply. These experiments, called deep inelastic scattering, were the first direct evidence that the proton has internal structure, that it is made of smaller constituents. Those constituents were the quarks. The sharp deflections were the quarks' fingerprints, just as the ricocheting projectiles had once been the nucleus's fingerprint. We had found the proton's parts without ever taking it apart, but confinement is only half of the strange behavior of the strong force, and the other half is just as important for understanding the proton. We have said that the force grows stronger as quarks move apart. The flip side of that statement is that the force grows weaker as quarks move closer together. And this has a name too. It is called asymptotic freedom, and it earned the physicists who discovered it the Nobel Prize because it solved a puzzle that had seemed almost paradoxical. When quarks are very close together, packed tightly, the strong force between them becomes feeble, almost gentle, and the quarks behave almost as if they were free, barely feeling the force at all. But as they drift apart, the force ramps up, growing and growing until the flux tube tension takes hold and confinement clamps down. So the strong force is weak at short distances and strong at long distances, the exact reverse of every force in our daily experience. Picture then what life is like for a quark inside a proton. When it is close to its partners, the force on it is weak, so it is nearly free to roam, and it does roam, moving at tremendous speed within the confines of that tiny volume. But the moment it strays toward the edge, the moment it tries to leave, the force surges and hauls it back, like a dog on an invisible elastic leash that is slack near the center, but yanks hard the instant the animal reaches the boundary. The quarks inside a proton are simultaneously nearly free and utterly trapped, free to move within, never free to leave. They rattle around at relativistic speeds in the interior, feeling little restraint until they approach the walls of their prison, at which point the full fury of confinement asserts itself and pulls them back into the fold. This is the dynamic, restless, energetic reality inside the proton. Not three calm marbles, but three captives racing around a cell whose walls push back harder the closer you get to them. This tug of war between the two behaviors is what gives the proton its size. You might wonder why the quarks do not simply collapse together, piling into the very center where the force is weakest and they are nearly free. They would, if confinement were the only rule. But the same quantum mechanics we met earlier forbids it. Squeeze the quarks into a smaller space and you force them to move faster, and faster motion means more energy, which resists the squeezing. So the quarks cannot fall to the center, and the surging force will not let them flee the edges. The proton settles at a size where these two pressures balance, about 1 femtometer across, the truce line between freedom and confinement. And the walls themselves, the flux tubes and gluon fields, are not static either. Remember that gluons interact with each other. The interior of the proton is therefore not just three quarks connected by neat tubes. It is a seething, self-reinforcing mesh of gluons emitting more gluons, fields tangling with fields, the whole structure constantly fluctuating, reshaping, churning. The gluon fields are not the passive scaffolding of the proton. They are an active, energetic, roiling medium in their own right, denser and more energetic in many respects than the quarks they bind. They are the storm within the storm. So let us assemble the full picture of the proton as the strong force reveals it. We have three valence quarks, racing at near light speed within their confinement, nearly free in the center, but bound absolutely by the surging force at the edges. We have the constantly fluctuating sea of quark-antiquark pairs, born from the energy of stretched and tangled fields and annihilating back into them. And we have the dominant, dense, self-interacting swarm of gluons, weaving the flux tubes, filling the interior with intense field energy, forever interacting with themselves and refusing to settle. All of this is packed into a region 1 femtometer across, held together by a force that grows stronger with distance, a force that has converted the proton from a quiet container into a perpetual, raging, high-energy machine. The proton does not hold still. It cannot hold still. The strong force makes stillness impossible. Every proton in the universe, including the trillions upon trillions inside your own body at this very moment, is an inferno of bound motion and field energy that has been raging without pause from the instant the particle first came into being, and that will not cease for as long as the proton endures. Now we are in a position to feel, with full force, why the proton is so much heavier than its quarks. We have established that the interior is bursting with energy. There is the kinetic energy of the racing quarks, energy of motion that vastly exceeds their tiny rest masses. There is the energy stored in the flux tubes, that 14-ton tension running through tubes of pure strong force field, energy that grows with every stretch and lives in the very structure of the binding. There is the energy of the self-interacting gluon swarm, the field energy of the storm within the storm. And there is the energy of the constantly materializing and annihilating sea. Every one of these is a reservoir of energy, packed densely into that femtometer-wide volume. And every one of them, through the equivalence of energy and mass, contributes weight to the proton. The mass we measure on the scale, the 938 mega-electron volts, is the bookkeeping total of all this bound energy. The proton is heavy because the strong force has filled it with energy, and energy weighs. And yet, even now, even after all of this, there is a paradox sitting right at the center of the picture, and an honest accounting forces us to confront it. We have just said that the gluon fields dominate the interior of the proton, that they carry tremendous energy, and that they are central to where the proton's mass comes from. But here is the troubling fact. Gluons have no mass. None at all. A gluon, considered by itself, is a massless particle, exactly like the photon. It has zero rest mass. It is, in that sense, a thing made of pure motion and field, with no intrinsic heft whatsoever. So how can a collection of massless gluons contribute mass to the proton? How can you build something heavy out of ingredients that individually weigh nothing? It seems almost contradictory. Add 0 to 0 to 0 a billion times over, and surely you should still get 0. Massless plus massless plus massless ought to equal massless. And yet the gluon fields are central to the proton's mass. Something here demands explanation, and it is not a small something. It is the very heart of the puzzle. This is the paradox we must now resolve, and it is genuinely one of the most beautiful resolutions in all of physics. How do massless gluons, and for that matter the energy of motion of nearly massless quarks, combine to produce the very real, very fixed, very weighable mass of the proton? How does a system built largely from massless and nearly massless ingredients end up with a definite mass shared identically by every proton in the cosmos? The answer lies in understanding something profound and subtle about the relationship between energy and mass, something far deeper than the familiar slogan that energy equals mass. It lies in understanding what mass actually means for a system of many parts, as opposed to a single particle, and in understanding how the energy of massless things, when bound and confined, becomes the permanent property we call mass. We have built the engine. We have seen the strong force in all its strangeness, the force that grows with distance, the force that confines quarks forever, the force that fills the proton with raging energy through flux tubes and self-interacting gluon fields. We have seen that this energy must somehow be the source of the missing 99% of the proton's mass. But we have also uncovered the paradox that the gluons carrying so much of that energy are themselves massless. To turn our picture from a compelling story into a genuine understanding, we have to confront that paradox head-on. We have to understand precisely how energy becomes mass, how massless becomes massive, how the furious motion and tension inside the proton crystallize into a fixed number on a scale. That is the deepest part of this story, the place where the equivalence of energy and mass shows its true and most astonishing face. And it is exactly where we are headed next. Here is a fact that sounds impossible the first time you hear it. You can take two things that each weigh nothing, combine them, and the combination weighs something. Two massless ingredients bound together produce a massive whole. This is not a trick of language, and it is not a paradox to be explained away. It is one of the deepest truths in physics, and it is the precise mechanism by which a proton, built largely from massless gluons and nearly massless quarks, ends up weighing so much. Tonight, we are going to understand exactly how 0 plus 0 can equal something real and weighable. And when we do, the entire mystery of the proton's mass will finally come into focus, not as a slogan, but as a genuine mechanical understanding of how the universe actually works. To get there, we have to go back to the most famous equation in all of science and understand what it really says, because almost everyone has heard it, and almost no one has been told the full truth about it. Energy equals mass times the speed of light squared. You have seen it. It is printed on t-shirts and coffee mugs, and the usual story told about it is that it means mass can be converted into energy, which is how nuclear bombs and nuclear reactors work, turning a little bit of mass into a tremendous amount of energy. That is true as far as it goes, but it is only half the story, and it is the less interesting half for our purposes. The equation does not only say that mass can become energy, it says that energy can become mass. More precisely, it says that energy and mass are the same thing, measured in different units, related by a conversion factor, the speed of light squared, which is simply an enormous number. Wherever you find energy, you find mass. Wherever you find mass, you find energy. They are not two separate quantities that can be swapped under special circumstances. They are one quantity wearing two different labels. But there is a subtlety in that equation that is almost always glossed over, and that subtlety is the entire key to the proton. The version printed on the mugs, energy equals mass times the speed of light squared, is actually a simplified form. It applies to an object that is sitting still. The complete equation, the one that physicists actually use, has an extra piece in it that accounts for motion. The full relationship says that the total energy of an object depends on two things. It depends on its rest mass, the intrinsic mass it has when standing still, and it depends on its momentum, which is to say, on how it is moving. The complete equation ties together energy, rest mass, and motion into a single relationship. And it is within that complete relationship, the one that includes motion, that the secret of the proton's mass is hidden. Let us approach the secret carefully, because it requires us to be precise about a distinction that everyday language completely blurs. We need to distinguish between the mass of an individual particle and the mass of a system made of many particles. These are not the same kind of thing. And confusing them is exactly why the simple addition of 3 quark masses gave us the wrong answer back at the very beginning. For a single, isolated particle, mass is simple. It is an intrinsic property, the rest mass, baked into what the particle is. An electron has a certain rest mass. An up quark has a certain rest mass. This is a fixed, unchanging number that belongs to the particle itself. So far, so familiar. But now consider a system, a collection of particles interacting, moving, bound together. What is the mass of the whole system? Here is where intuition fails us, because we instinctively assume the mass of the whole is just the sum of its parts. We assume mass is like counting marbles. 3 marbles weigh 3 times as much as 1 marble. The whole is the sum of the parts. This assumption is so natural that we never question it. And it is wrong. For a system of particles, the mass of the whole is not the sum of the masses of the parts. The mass of a system is determined by the total energy contained within that system when the system as a whole is at rest. Read that again, because it is the entire resolution of our paradox. The mass of a system is its total internal energy divided by the speed of light squared, not the sum of its parts, not the sum of the rest masses of its constituents. The total energy. And total energy includes everything. It includes the rest masses of the parts, yes, but it also includes the kinetic energy of all the parts as they move around inside the system. And it includes the energy stored in the fields that bind the parts together, the energy of the forces acting between them. Every form of energy contained within the system contributes to the system's mass. This quantity, the mass that a whole system has by virtue of its total internal energy, has a name. Physicists call it the invariant mass of the system. And the invariant mass of a system can be, and very often is, far larger than the sum of the rest masses of its individual pieces, precisely because the system contains energy of motion and energy of fields that the bare rest masses do not include. Now watch what this does to our paradox about massless gluons. We were troubled by the idea that gluons have no mass, and yet they contribute to the proton's mass. We were stuck on the arithmetic that 0 plus 0 plus 0 ought to equal 0. But we were committing exactly the error we just identified. We were treating the proton's mass as a sum of the masses of its parts. It is not. The proton's mass is the total energy of the proton as a system, when the proton is at rest as a whole. And here is the beautiful, crucial point. A gluon may have 0 rest mass, but a gluon is never at rest. A massless particle can never be still. It always moves at the speed of light, and it always carries energy. A gluon racing through the interior of the proton, carrying energy in its motion and its field, contributes that energy to the total energy of the proton. And that energy, through the equivalence of energy and mass, contributes to the proton's mass. The gluon has no mass of its own, but it carries energy, and energy is what builds the mass of the system. So the resolution is this. You do not build the proton's mass by adding up the masses of massless gluons, which would indeed give 0. You build it by adding up the energy of those gluons, which is enormous. Massless ingredients contribute nothing to the sum of rest masses, but they contribute their full energy to the total energy of the system, and it is the total energy that determines the mass. 0 rest mass, but abundant energy. And abundant energy means abundant mass for the bound system. The paradox dissolves completely once you understand that mass, for a system, is energy, and that massless things still carry energy. Let me make this concrete with a simpler example, because the idea is so important that it deserves to be seen from more than one angle. Imagine a sealed, perfectly reflecting box, a box whose interior walls are perfect mirrors so that nothing can get in or out. Now imagine you fill this box with light. Photons bouncing around inside are trapped by the mirrors. Light is made of photons, and photons, like gluons, have exactly 0 rest mass. So you have filled your box with massless particles. Here is the astonishing consequence. The box full of light weighs more than the empty box. Measurably more. You have added nothing with any rest mass. You have added only massless light, and yet the box has become heavier. Why? Because the box now contains more energy, the energy of all that trapped light, and that energy contributes to the invariant mass of the box plus light system. The light has no mass, but the system of light trapped in a box has mass, because the system has energy. If you put that box on a scale, it would read heavier than before, by an amount exactly equal to the energy of the light divided by the speed of light squared. And notice the strangeness. Not one of those photons is ever at rest, yet the scale weighs their restless energy all the same, exactly as it weighs the racing gluons in a proton. You can build mass out of trapped massless light, and that is, in essence, exactly what the proton does. The proton is a box, made not of mirrors, but of the confining strong force, and trapped inside it is a tremendous quantity of energy, the energy of racing quarks and swarming massless gluons. That trapped energy is the proton's mass. This is the heart of the matter, and it is worth pausing to appreciate how it inverts our everyday picture of what mass is. We tend to think mass comes from stuff, from substance, from heavy material packed into a volume. But the box of light shows us that mass comes from confined energy. It is the trapping, the binding, the confinement that turns energy into the property we call mass. Free light streaming through space does not constitute a massive object. But the moment you trap that light, bind it, hold it in place so that it cannot escape, the system you have created has mass. Confinement is the alchemy that turns energy into mass. And the strong force, as we saw, is nature's most powerful confiner. It traps the energy of quarks and gluons inside a femtometer-wide volume and refuses, absolutely, to let any of it escape as a free particle. That relentless confinement is precisely why the trapped energy manifests as the substantial, weighable mass of the proton. Now, I have been careful throughout to avoid letting any of this collapse into a slogan, and I want to keep being careful here, because there is a tempting oversimplification lurking nearby. It is tempting to say that the proton's mass is just binding energy, and to leave it at that. But binding energy is a subtle idea, and saying it carelessly can actually lead you astray, so let us handle it properly. In most physical systems you have ever encountered, binding energy works in the opposite direction from what we have been describing. When things bind together, they usually release energy and become lighter, not heavier. Consider a hydrogen atom, a single proton with a single electron bound to it. The bound atom actually weighs slightly less than a free proton and a free electron considered separately. When the electron falls into orbit around the proton and binds to it, the system releases energy. That energy radiates away as light, and the bound atom that remains has slightly less total energy, and therefore slightly less mass, than its unbound ingredients. Binding, in this case, reduces mass. The same is true when protons and neutrons bind together into an atomic nucleus, releasing energy, the energy that powers the sun and that nuclear reactors harness. The bound nucleus weighs less than its separate parts. This is the ordinary, familiar behavior of binding energy. Bind things, release energy, lose mass. So if binding usually makes things lighter, how can the binding of quarks make the proton heavier? Why does the strong force inside the proton behave in the opposite way? This is exactly the kind of question that separates a real understanding from a slogan, and the answer is illuminating. In the ordinary cases, like the atom or the nucleus, the constituents start out free, with their own substantial masses, and binding lowers the total energy below the sum of those starting masses. But the quarks inside a proton are different in a profound way. They cannot start out free. Confinement forbids it. There is no such thing as a free, isolated quark sitting quietly with its rest mass, available to be brought together. The very state of being a quark is the state of being bound and confined. And the confining force, as we saw in detail, is one that requires enormous energy to maintain. The flux tubes, the self-interacting gluon fields, the relentless tension, all of these store vast quantities of energy as an inescapable feature of confinement itself. The strong force does not release energy when it binds quarks. It costs energy to confine them, and that energy lives inside the proton as part of its total energy, and therefore as part of its mass. The binding here is not a gentle settling that releases energy. It is a violent imprisonment that requires energy, and that required energy becomes the proton's mass. So when people say the proton's mass comes from binding energy, what they really mean, said carefully, is this. The proton's mass is the total energy of the confined system of quarks and gluons, an energy dominated by the kinetic energy of the quarks and the field energy of the gluons that the strong force demands in order to confine everything. It is not binding energy in the sense of energy released by coming together. It is the energy inherent in maintaining a confined, dynamic, high-energy bound state. That distinction matters, and getting it right is the difference between understanding the proton and merely repeating a phrase about it. Let us now put real numbers to the picture so we can see exactly how the accounting works out. The measured mass of the proton is about 938 megaelectron volts. We established that the rest masses of the three valence quarks, 2 up and 1 down, total only about 9 megaelectron volts. That 9 is real, it is there, and it counts toward the proton's total energy. But it is barely 1% of the total. Where is the rest? It is distributed among the other forms of energy in the system. A large share is the kinetic energy of the quarks, the energy of their relentless near-light-speed motion within their confinement. Another large share, in many accountings the dominant share, is the energy of the gluon fields, the self-interacting swarm that builds the flux tubes and fills the interior. And a further share lives in the sea of quark-antiquark pairs constantly being created and annihilated. Add up the rest masses of the quarks, the kinetic energy of all the quarks, the field energy of all the gluons, and the energy of the fluctuating sea, and the grand total comes to 938 megaelectron volts. That grand total, the total energy of the bound system at rest, is the proton's mass. The 1% that is quark rest mass, plus the 99% that is the energy of motion and fields, together make the whole. And I want to be precise about one thing here, because earlier I flagged that we should avoid assigning a single, misleading percentage to any one component. It is genuinely difficult to cleanly divide the proton's energy into neat, separate buckets and say, this exact percent is quark motion, this exact percent is gluon field. The reason is that these contributions are not independent, tidy compartments. The quarks and gluons are interacting constantly, exchanging energy ceaselessly, and the way you divide up the total energy can depend on the details of how you choose to look at the system. What is rock solid, what no physicist disputes, is the headline fact. The quark rest masses contribute only about 1%. The overwhelming remainder is the energy of the dynamic, confined, strongly interacting system, energy of motion and energy of fields. The precise split between quark kinetic energy and gluon field energy within that remainder is a more delicate question, and the honest answer is that they are deeply intertwined. But the core conclusion stands unshaken. Nearly all the proton's mass is the energy of the strong interaction at work, not the intrinsic mass of the quarks. Now I want to return to the equation one more time, with everything we have learned, because we can now read it with a much deeper understanding. The complete energy-mass-momentum relationship tells us that the energy of a system depends on its rest mass and its motion. For the proton as a whole, sitting at rest on our laboratory scale, its energy is simply its mass times the speed of light squared. That is the proton's total rest energy, and it is what we weigh. But that total rest energy of the proton as a single object is built up from the inside, out of the energies of all its constituents, the rest energies of the quarks, plus the kinetic energies of the quarks, plus the field energies of the gluons. The proton, viewed from outside, is a single object at rest with a definite mass. The proton, viewed from inside, is a roaring system of energy. And these two views are reconciled by the equivalence of energy and mass. The internal energy, summed up, is the external mass. The storm within, totaled, is the weight without. There is something almost philosophically startling about this, and it deserves to be felt, not just stated. It means that the mass of ordinary matter is, in a very real sense, a frozen form of energy. Or perhaps better, a confined, self-sustaining form of energy. The proton does not contain its mass the way a jar contains marbles. The proton is a process, an ongoing, ceaseless process of quarks racing and gluons swarming and fields tensing and pairs flickering, and the mass is the total energy of that process. If the process ever stopped, if the motion ever ceased, and the fields ever relaxed, the mass would be gone. But the process never stops, because the strong force never relents. The confinement is permanent, and so the energy is permanent, and so the mass is permanent. Every proton is a perpetual engine of bound energy, and its weight is the measure of how much energy it has trapped and kept running. And this is why I have insisted, again and again, that we are not saying mass is created from nothing. The energy inside the proton is utterly real. It was put there when the proton formed, drawn from the energy available in the early universe, or in whatever process created the particle. It is conserved. It is governed by exact laws. It is not conjured from emptiness. What we are saying is that energy, which was always real and always present, takes the form of mass when it is bound and confined into a system at rest. The proton's mass is not a creation of something from nothing. It is a manifestation of energy as mass, made permanent by confinement. There is all the difference in the world between mass from nothing, which would be magic, and mass from confined energy, which is physics. This story is, from beginning to end, physics. We can now also see clearly why the simple addition we did at the very start was doomed to fail. When we added the rest masses of the three quarks and got 9 mega-electron volts, we were committing the error of treating the proton's mass as the sum of the masses of its parts. We now know that the mass of a system is not the sum of the masses of its parts. It is the total energy of the system. The sum of the rest masses leaves out the kinetic energy of the quarks, the field energy of the gluons, the energy of the sea, all of it, the entire 99%. Our 9 mega-electron volts was not wrong as a sum of rest masses. It was simply answering the wrong question. The right question was never, what do the parts weigh? The right question was always, how much energy does the bound system contain? And the answer to that question is 938 mega-electron volts, the true mass of the proton. So we have resolved the paradox completely. Massless gluons build mass because they carry energy, and the mass of a system is its total energy, not the sum of its parts masses. Confinement turns that energy into permanent mass, just as a box of mirrors would gain weight from the light trapped inside it. The proton is heavy because it is a confined system bursting with the energy of the strong interaction, and that energy, totaled up, is its mass. We have gone from a baffling factor of 100 discrepancy to a clear and beautiful mechanism. The mass of nearly all visible matter is the energy of confined, strongly interacting quarks and gluons, expressed as mass through the deepest principle of relativity. And yet, two important questions remain before our picture is truly complete. The first is the one we flagged but set aside. We have said that the quarks have rest masses at all, that 1% that does come from the quarks themselves. But where do those rest masses come from? What gives a quark its intrinsic mass in the first place? We touched on the answer earlier, a famous field with a famous name, but we have not yet seen how it works, or, crucially, how it differs from the mass-generating mechanism of the strong force we have spent so long understanding. The second question is even more demanding, and it is the question a true skeptic should be asking right now. This is a wonderful story, beautifully self-consistent, but how do we actually know it is true? How can anyone calculate the mass of the proton from these principles and confirm that the theory of the strong force really does produce 938 mega-electron volts and not some other number? We cannot pull a quark out and weigh the pieces. So how is this verified rather than merely asserted? The answer to that involves one of the most impressive feats of computation in the history of science, in which physicists build a tiny universe inside a supercomputer and weigh a proton from scratch. Those two threads, the origin of the quark's own small masses, and the extraordinary way physicists prove all of this from first principles, are exactly where we turn next. In 2012, thousands of physicists gathered in anticipation as a laboratory beneath the border of France and Switzerland announced the discovery of a particle that had been hunted for nearly 50 years. The headlines called it the God particle. They said it was the thing that gives everything its mass. And so, if you have been following our story carefully, you might reasonably conclude that we have been leading you astray this whole time. We have spent all this effort explaining that the proton's mass comes from the energy of the strong force. And now, here is a particle, splashed across every newspaper in the world, described as the source of all mass. Surely the Higgs is the real answer, and the strong force is a sideshow. That conclusion would be understandable, and it would be almost entirely wrong. Tonight we are going to see exactly what the Higgs field does and what it does not do, why it matters enormously and yet accounts for almost none of your weight. And then we are going to see the truly astonishing way physicists proved the entire story of the proton's mass by building a universe inside a computer and weighing a proton from nothing but the bare laws of nature. Let us begin with the Higgs field, because it is genuinely one of the great achievements of modern physics, and it deserves to be understood properly, not dismissed and not overhyped. To understand what the Higgs does, we have to return to a question we deliberately left hanging. We said that the quarks have rest masses, small as they are. The up quark has its 2.2 mega-electron volts, the down quark its 4.7. We treated those numbers as given, as intrinsic properties of the quarks. But why do the quarks have those masses at all? Why is the up quark not simply massless, like the gluon or the photon? Where does a quark's intrinsic, built-in rest mass actually come from? That is the question the Higgs field answers. And it answers it for a whole family of fundamental particles, not just quarks. The electron, for instance, also has a rest mass, and it too comes from the Higgs. Here is the idea. The Higgs field is not a particle, at least not first and foremost. It is a field, something that fills all of space, present everywhere, including the room you are sitting in right now and the space between the stars. Most fields in physics are zero when nothing is happening, when there is no source to excite them. The electric field, for example, is zero in a region with no charges around. But the Higgs field is different. The Higgs field has a value that is not zero even in completely empty space. It sits at a constant, non-zero value everywhere, all the time, as a permanent feature of the vacuum itself. The universe is soaked in the Higgs field, the way a sponge is soaked in water, uniformly, everywhere, by default. And certain fundamental particles as they move through this ever-present field, interact with it. They feel it. The field, in a sense, resists their motion, and this resistance manifests as the particle having mass. The more strongly a particle interacts with the Higgs field, the more the field resists it, and the greater its rest mass. A particle that interacts strongly with the Higgs field is heavy. A particle that interacts weakly with it is light. And a particle that does not interact with the Higgs field at all, like the photon or the gluon, has no rest mass whatsoever and sails through the field completely unimpeded, which is precisely why those particles are massless and always travel at the speed of light. You will sometimes hear this described with an analogy, and like all analogies, it is imperfect, but it captures something. Imagine the Higgs field as a room full of a thick, uniform medium, and imagine different particles trying to move through it. Some particles are like a sleek object that slips through with barely any drag, and these acquire little mass. Others are like a bulky object that has to push through, meeting resistance at every step, and these acquire large mass. The resistance to being pushed through the field is, loosely, what we experience as the particle's mass, its inertia, its reluctance to be accelerated. The analogy breaks down if you push it too hard, because the Higgs mechanism is far more subtle and mathematical than thick syrup, but the essential lesson survives. Mass, for a fundamental particle, is a measure of how strongly it talks to the Higgs field that fills all of space. So what about the famous particle discovered in 2012, the one the newspapers got so excited about? That particle is the Higgs boson, and it is not the same thing as the Higgs field, though the two are intimately related. The field is the thing that fills all of space and gives particles their masses. The boson is what you get when you disturb that field, when you poke it hard enough to make a ripple in it, a localized vibration of the field itself. Finding the Higgs boson was the way physicists proved that the Higgs field is really there. If you can make a ripple in something, the something must exist. For decades, the Higgs field was a theoretical prediction, an elegant idea that explained where particle masses come from, but had never been directly confirmed. To confirm it, physicists needed to create a ripple in the field, a Higgs boson, and detect it. That required smashing particles together at tremendous energies in an enormous machine. And in 2012, after research lasting nearly half a century, they finally succeeded. The detection of the Higgs boson confirmed that the Higgs field exists and that the mechanism giving fundamental particles their masses is real. It was a monumental achievement, fully deserving of its Nobel Prize. The God particle nickname, by the way, was something most physicists disliked, a piece of publishing sensationalism rather than a scientific description. But the underlying discovery was as important as the hype suggested, just not for the reason most people think. Now we arrive at the crucial point, the point that reconciles everything. The Higgs field gives fundamental particles their rest masses. It gives the up quark its 2.2 mega-electron volts. It gives the down quark its 4.7. It gives the electron its mass. These are real, and they are genuinely the work of the Higgs. But look at what those numbers are. They are precisely the tiny rest masses that we added together at the very beginning of our journey and found to total only about 9 mega-electron volts for the proton's 3 quarks. They are the 1%. The Higgs field is responsible for that 1% of the proton's mass, the small sliver that comes directly from the intrinsic masses of the quarks. The Higgs gives the quarks their rest masses, and those rest masses contribute their modest share to the proton's total energy. But the Higgs has almost nothing to do with the other 99%. The overwhelming bulk of the proton's mass, as we have spent this whole journey establishing, comes from the energy of the strong force, the kinetic energy of the confined quarks, and the field energy of the gluons. That energy is governed by quantum chromodynamics, the theory of the strong interaction, and it has nothing to do with the Higgs field at all. So both things are true at once. and there is no contradiction. The Higgs field genuinely gives mass to fundamental particles, and the strong force genuinely provides nearly all the mass of the proton. The resolution is simply that these two mechanisms operate at different levels and account for different portions of the total. The Higgs is the source of the small intrinsic masses of the individual quarks. The strong force is the source of the vast energy of the bound system. The Higgs sets the table by giving the quarks a little mass to begin with. The strong force provides the feast. If you wanted a single sentence to carry away, it would be this: the Higgs field gives the quarks their masses, but the quarks' masses are not where the proton's mass comes from. And here we can see something genuinely profound about the nature of ordinary matter. If the Higgs field were somehow switched off, if it vanished and the quarks lost their intrinsic rest masses entirely, the proton would not vanish along with them. It would lose only about 1% of its mass. The quarks would become massless, but they would still be confined, still racing around inside the proton, still bound by the strong force, still carrying enormous kinetic energy, still swarmed by gluon fields. The proton would still have nearly all of its mass, because nearly all of that mass was never the quark's rest mass to begin with. The matter around you, the mass of your body, the weight of the world, would remain almost entirely intact, even without the Higgs. Your mass does not come from the Higgs field. It comes, to about 99%, from the energy of the strong interaction confined inside your protons and neutrons. The Higgs is essential to the structure of physics in countless ways, but it is not the reason you have weight. The reason you have weight is the strong force, raging in every proton and neutron in your body, its energy made permanent by confinement and expressed as mass. This is a beautiful and somewhat humbling conclusion, but a careful, skeptical mind should not accept it just because it is beautiful. Beauty is not proof. We have told a compelling, self-consistent story about quarks and gluons and energy and confinement, and it all hangs together elegantly. But how do we actually know it is correct? How does anyone confirm that the theory of the strong force, applied to its constituents, really produces a proton with a mass of 938 megaelectronvolts, and not some other number? We have said over and over that you cannot pull a quark out of a proton and weigh it, so we cannot check the theory by isolating the parts. The whole storm is locked inside, inaccessible to direct dissection. How then can the claim be tested? How do we move from a lovely narrative to a verified scientific fact? The answer is one of the most remarkable computational achievements in the history of science, and it has a name that sounds technical but describes something genuinely extraordinary. It is called lattice quantum chromodynamics. And what it amounts to, in spirit, is this. Physicists take the fundamental equations of the strong force, the equations of quantum chromodynamics, the deepest known description of how quarks and gluons behave, and they solve those equations directly, from scratch, using enormous supercomputers to calculate what the mass of the proton should be. They do not put the answer in. They do not assume the proton's mass. They start only with the basic laws governing quarks and gluons, the same laws written down by theorists decades ago, and they grind through the staggering mathematics to see what mass those laws predict for a proton. It is, in effect, building a tiny piece of the universe inside a computer, populating it with quarks and gluons obeying the true laws of the strong force, and then weighing the proton that emerges. Let me explain how this is possible, because the equations of quantum chromodynamics are so fearsomely complicated that they cannot be solved with pencil and paper, not even approximately, in the regime that matters for the proton. The strong force, recall, becomes powerful at the distances relevant inside a proton, which means the usual mathematical tricks physicists use for weaker forces simply fail. There is no neat formula you can write down and evaluate. The interactions are too strong, too tangled, too rich with gluons emitting gluons and fields interacting with fields. For a long time, this made the theory almost uncomputable in practice. Physicists were confident the theory was correct, but proving that it produced the right proton mass seemed beyond reach. The mathematics was just too hard. The breakthrough idea was to stop trying to treat space and time as smooth and continuous, and instead to chop them up into a grid. This is the lattice in lattice quantum chromodynamics. Imagine taking the tiny region of space and time where a proton lives and replacing the smooth continuum with a fine grid of discrete points, like the pixels of a digital image, arranged in a regular lattice in all 4 dimensions, 3 of space and 1 of time. The quarks live on the points of this grid, and the gluon fields live on the links connecting neighboring points. By turning the smooth, infinite, uncomputable continuum into a finite grid of points, physicists turn the impossible equations into something a computer can actually handle. The computer can keep track of the quark and gluon fields at every point on the grid, apply the laws of quantum chromodynamics step by step, and compute the behavior of the whole system numerically by brute force, crunching through astronomical numbers of calculations. This is staggeringly demanding work. The grids must be extremely fine to capture the real physics, with many points packed closely together, because if the grid is too coarse, it misses the fine structure of the fields and gives the wrong answer. And quantum mechanics adds a further layer of difficulty, because in quantum theory, you cannot simply compute a single configuration of the fields. You have to account for every possible configuration the fields could take, weighted appropriately, summing over an almost inconceivable number of possibilities. The computational cost is immense. These calculations consume some of the most powerful supercomputers on Earth, running for months, performing quadrillions of operations, just to compute the properties of a single proton from first principles. It is among the most intensive number-crunching tasks anyone has ever attempted. Whole specialized computing facilities have been built, largely to make such calculations feasible. It is worth knowing how recent this triumph actually is. For decades, physicists believed the theory of the strong force was correct, but they simply could not prove it produced the right proton mass, because the computation was beyond any machine in existence. It was only in the late 2000s, after the arrival of sufficiently powerful supercomputers, that the calculation was finally carried through, and the masses of the proton, the neutron, and their relatives emerged from the bare equations. There is a particular difficulty in these calculations that is worth understanding, because it reveals something deep about why the strong force is so hard to compute and how physicists cleverly get around it. In quantum theory, as we noted, you cannot simply compute one arrangement of the fields and call it the answer. The proton is not in any single definite configuration. It is, in the strange way of quantum mechanics, in a blend of all possible configurations at once, every possible arrangement of quarks and gluons contributing to the whole. To compute the proton's properties honestly, you would have to add up the contributions of every conceivable configuration the fields could take, and the number of possible configurations on even a modest grid is so vast that no computer, not now and not ever, could examine them one by one. There are more possible field arrangements than atoms in the observable universe. Listing them all is hopeless. So physicists do something resembling what a pollster does when trying to gauge the opinion of an entire nation. A pollster cannot ask every single person, so instead they sample, carefully selecting a representative subset and using it to estimate the whole. The lattice physicists do the same with the proton's configurations. Rather than examining every possible arrangement of the fields, they use the computer to randomly sample arrangements, but cleverly, drawing each sample with a probability matched to how much that arrangement actually matters to the final answer. Configurations that contribute heavily are sampled often. Configurations that barely matter are sampled rarely. By generating thousands upon thousands of these weighted random samples and averaging over them, they estimate the proton's true properties without ever having to examine the impossibly large total. The method is statistical, like a poll, and like a poll, its answer comes with a small, quantifiable uncertainty that shrinks as more samples are taken. This is why these calculations devour so much computer time. Every additional sample sharpens the answer a little more, and physicists run them for months to drive the uncertainty down low enough to make a confident prediction. The proton's mass, computed this way, emerges not as a single tidy formula, but as a hard-won statistical result, averaged over a vast number of simulated quantum worlds. And here is the payoff, the moment that should make the hair on your arms stand up. When physicists carry out these lattice calculations, starting only from the fundamental equations of the strong force, putting in nothing but the basic properties of quarks and gluons, and grinding through the mathematics on their supercomputers, the proton mass that comes out is about 938 mega-electron volts. The calculation, done from scratch, with no knowledge of the answer fed in, reproduces the measured mass of the proton. The theory works. The strong force, applied through its true equations to its quarks and gluons, really does produce a proton with exactly the mass we weigh in the laboratory. This is the proof. This is how we know the story is true and not just a pretty narrative. We can compute the proton's mass from the bare laws of nature, and the laws deliver the right answer. It is worth pausing to appreciate just how complete this verification is. The lattice calculations do not only get the proton's mass right, they get the masses of a whole family of related particles right, the neutron, and a whole zoo of other particles built from quarks and gluons, all computed from the same fundamental equations, all matching the measured values. When a theory, fed nothing but its basic laws, correctly predicts the masses of dozens of particles across the board, you can be confident the theory is capturing something real and deep about nature. And crucially for our story, these calculations confirm the breakdown of where the mass comes from. They show, in detail, that the quark rest masses account for only a small fraction of the total, and that the overwhelming bulk arises from the energy of the quark's motion and the gluon fields, exactly as our whole journey has described. The picture of the proton as a confined storm of energy is not a hand-waving story told to make the physics palatable. It is what the equations themselves say, verified to high precision by some of the most demanding computations ever performed. There is something almost poetic about this method of proof. We could not take the proton apart in the laboratory to examine its pieces because confinement forbids it. The quarks will never be pulled free and weighed individually. So instead, physicists built a proton inside a computer, a faithful replica governed by the true laws, and took that one apart mathematically, examined its energy budget, and weighed the whole. Where nature locked the proton shut, computation pried it open. The supercomputer became the instrument that let us see inside a particle that can never, in principle, be cracked open in the real world. It is a triumph not just of physics, but of the marriage between physics and computation. A demonstration that when direct observation fails, the laws of nature, faithfully simulated, can reveal what is hidden. So let us now gather the whole story together, because we have travelled a long way and the full picture is worth seeing all at once. We began with a contradiction. Add up the rest masses of the proton's 3 quarks, and you get about 9 mega-electron volts. Yet the proton weighs about 938. 99% of the mass was missing. We discovered that the simple picture of three quarks sitting in a bag is profoundly incomplete. A proton is a churning, ferocious system containing three valence quarks racing at near light speed, a flickering sea of quark-antiquark pairs constantly appearing and vanishing, and a dense, dominant swarm of self-interacting gluon fields. We learned about the strong force, the strangest force in nature, the force that grows stronger with distance, the force whose gluons interact with each other and bundle the field into taut flux tubes of enormous tension. We saw how that force confines the quarks absolutely, so that they can never be isolated, because trying to pull one free simply converts the energy of separation into new particles. We confronted the paradox that the gluons carrying so much of the proton's energy are themselves massless, and we resolved it by understanding that the mass of a system is its total energy, not the sum of its parts' masses, so that even massless gluons, by carrying energy, build the mass of the whole, just as a box of trapped light weighs more than an empty box. We saw that confinement is the alchemy that turns energy into permanent mass. We carefully distinguished this from the binding energy of atoms and nuclei, understanding that the strong force costs energy to confine its quarks, and that this energy is the proton's mass. We placed the Higgs field correctly as the source of the quark's small intrinsic rest masses, the 1%, and not the source of the proton's bulk. And finally, we saw how lattice quantum chromodynamics proves the whole edifice, computing the proton's mass from first principles and arriving at the measured value, confirming that nearly all the mass is the energy of the strong interaction at work. And now, step back and feel the full weight of what this means, because it reaches far beyond the proton. Protons and neutrons make up the nuclei of every atom, and the nuclei carry essentially all the mass of every atom, since the electrons are nearly a couple thousand times lighter than the protons and neutrons and contribute almost nothing to the total. So the mass of every atom is, to overwhelming degree, the mass of its protons and neutrons. And the mass of those protons and neutrons is, to about 99%, the energy of the strong force confined within them, which means that nearly all the mass of every ordinary object in the universe, every rock, every ocean, every planet, every star, every living body, is not really the mass of fundamental particles at all. It is emergent energy, the energy of the strong interaction, trapped and made permanent by confinement, expressed as mass through the equivalence of energy and mass. The solidity of the world, the heft of things, the very substance of ordinary matter, is overwhelmingly bound energy. When you hold something heavy and feel its weight pressing into your hand, you are feeling, almost entirely, the energy of the strong force raging inside countless protons and neutrons. Energy that has been locked in motion since the early universe, and will remain so for as long as that matter exists. There is a moment in the history of the universe when all of this mass came into being, and it is worth visiting, because it puts the strong force's role in ordinary matter into its grandest possible perspective. In the very first instance after the universe began, in the first millionths of a second, conditions everywhere were so hot and so dense that protons and neutrons could not exist at all. The temperature was so extreme that quarks and gluons could not be confined into bound particles. They roamed freely, all of them together, in a searing, universe-filling soup that physicists call the quark and gluon plasma. There were no protons then, no neutrons, no atoms, nothing built from confined quarks. There was only the plasma, a state of matter so hot that the strong force, which today imprisons quarks so absolutely, could not hold them together against the sheer violence of the heat. And here is something remarkable. We have made that plasma again. In the most powerful particle colliders on Earth, physicists smash heavy atomic nuclei together at nearly the speed of light, and for the briefest possible instant, the collision reaches temperatures of trillions of degrees, hotter than the center of any star, hot enough to melt protons and neutrons back into the free quarks and gluons of the early universe. For a flicker of time, in a space smaller than a single atom, they recreate the state of everything as it was before mass switched on. The plasma exists for less than a trillionth of a second before it cools and the quarks snap back into ordinary particles. But we have seen it. We have briefly remade the conditions of the newborn cosmos and watched ordinary matter condense out of them. Then the universe expanded and cooled, as it has been doing ever since. And at a certain moment, a few millionths of a second in, the temperature dropped low enough that the strong force could finally take hold. Across the entire universe, almost simultaneously, the free quarks and gluons were swept up and confined, locked together into protons and neutrons for the first time. This is sometimes called the moment of confinement, and it is the moment when nearly all the mass of ordinary matter was effectively switched on. Before it, the constituents existed, but the bound energetic systems we call protons and neutrons did not, and so the mass that emerges from their confinement did not yet exist in that form. After it, the universe was populated with protons and neutrons, each one a tiny confined storm of strong force energy, each one carrying the emergent mass we have spent this whole journey explaining. Think about what that means. The mass of every atom in your body traces back to that instant, a few millionths of a second after the beginning of everything, when the cooling universe first allowed the strong force to confine its quarks. The mass was not built particle by particle over the long ages that followed. It was, in a sense, born almost all at once, in the universe's first heartbeat, when confinement switched on across all of space, and the energy of the strong force became locked into permanent mass. The weight of the world is nearly 14 billion years old, forged in the opening moment of the cosmos, and it has been raging quietly inside every proton and neutron ever since. This is perhaps the most surprising thing physics has discovered about ordinary matter. We are taught from childhood that matter is made of tiny particles, and we imagine those particles as little nuggets of substance, of stuff, of mass. But when we look closely at where the mass actually resides, we find that it is not in the nuggets at all. The fundamental particles, the quarks, contribute almost nothing. The mass lives in the relationships between them, in the energy of their confinement, in the storm of motion and field that the strong force sustains inside every proton and neutron. Mass, the most solid and substantial property we know, turns out to be, for ordinary matter, a manifestation of trapped energy and ceaseless internal motion. The substance of the world is, at its root, not substance at all. It is bound energy, given the face of mass. And so, the answer to our original question, where does a proton get most of its mass from, is now complete. And it is far more wonderful than the simple sum we attempted at the start. The proton gets a small sliver of its mass, about 1%, from the intrinsic rest masses of its quarks, which the Higgs field provides. And it gets the entire vast remainder, the other 99%, from the energy of its own internal storm, the kinetic energy of confined quarks, and the field energy of swarming gluons, all bound together by the strong force and made permanent through confinement. The proton's mass is, almost entirely, the weight of energy that cannot escape. It is the strong force made tangible. It is the universe demonstrating, in every atom of everything, that energy and mass are one, and that the solid world we know is built, overwhelmingly, from the trapped and tireless energy of the force that holds the smallest things together.